Good morning, students. Once again, I welcome you all for this session. Okay, let us move on to the next module, that is module number 3. Okay, limit state design of beams. Okay, so till now, module 1 and module 2, whatever we have studied, so that is nothing but the analysis. Okay, analysis of singly reinforced beam, doubly reinforced beam, and T beam. Okay, now let us start with this session with design of beams. Okay, so what do you mean by this design now? Analysis we already know, right? Whatever the load which is comes on the elements, okay, so that we have to calculate, or we have to calculate the moment of resistance of beams. But let us start with the design. Design is nothing but assessment of loads, whatever the load we are going to get. Okay, that load, from the load we are going to calculate the bending moment, and to resist this bending moment, what is the dimension of the beam required, size of the beam required, and reinforcement required we are going to calculate. So that is nothing but design of beams. Okay, so here onwards, that module number 3 will design the beams, that is singly reinforced beam, doubly reinforced beam, and T beams. And in module number 4 we will going to design slab and staircases, and in module number 5 we will going to design column and footings. Okay, so here onwards, module 3, 4 and 5 are totally a design of elements. Okay, first we will take this design of beams. Okay, now as we know, design of reinforced concrete beam element to resist a given system of external loads. So external loads will be coming on the beam. Okay, we are going to take these external loads. Okay, and to resist this external loads, what will be the size of the beam required, that we are going to assess. So that is called as design. So before going into the design, some practical rules we should know. Okay, so especially in the practical or actually construction, some important rules will be there. We have to follow the rules. As a engineer, as a civil engineers, we should know what are these important practical rules. Okay, first one is, right, so beam may be simply supported beam, or it may be a cantilever beam, or it may be a continuous beam. Okay, so there are three possibilities. So either you can design beam as a simply supported beam, or cantilever beam, or a continuous beam. Now for a simply supported beam or a slab, even if you can consider slab and beam, almost design will be same. For a simply supported beam or slab, the effective span, one important factor you have to consider is effective span. The effective span shall be taken as clear span plus effective depth. Okay, one first criteria is effective span is equal to clear span plus effective depth, or second criteria is the distance between the centers of bearings, whichever is less. So two criteria you have to consider for effective span. So effective span is equal to clear span plus effective depth of the beam, that will give one effective span. The second option is the distance between the centers of bearings. Bearings is nothing but the supports. Okay, so center of one support to the center of another support is called effective span. Out of these two criteria, which one is the less, that will be considered as the final effective span of the beam. Okay, this is the first important rule you have to remember. Okay, so two criteria you have to consider for effective span. First is clear span plus effective depth. Second is, okay, center to center of bearing. Out of these two, whichever is less, that will be the effective span. Then the second rule or second criteria, important points you have to remember is, for beams and slabs, okay, for beams as well as for slabs, the deflection is important, because these are the tension members. Okay, in tension members, because of bending moment, there will be a deflection. Okay, so based on the deflection, you have to design the beam. Okay, so you have to find out the what is the effective depth and overall depth of the beam required. So for beams and slabs, the vertical deflection limits may be generally assumed to be satisfied, provided that the span to depth ratio, this is important, span to depth ratio, okay, are not greater than the values obtained below. Okay, so some reference points you have to see. Okay, when you are assuming here, initially we have to assume the depth, remember. So in design, in the first step we have to assume the depth. Okay, so how to assume the depth? Okay, so that there should not be any repetition. Okay, so normally what we are going to do, span up to 10 meter. So if the beam length up to 10 meter, okay, so what you have to assume, you have to assume L by D ratio, that is small l divided by small d, that is small l is effective span and small d is effective depth. So L by D ratio we will going to assume. Okay, so how to assume? Now there are three possibilities. If the beam is cantilever beam, okay, right, if the beam is cantilever beam, then L by D you have to assume 7. L by D is equal to 7. So L is given in the problem, okay, and D we have to find out. So L by D is equal to 7, then D will you going to calculate. If it is cantilever beam, you have to assume L by D 7. If you are designing simply supported beam, L by D is equal to 20. Okay, L by D is equal to 20. And if it is a continuous beam, so if the beam is continuous over the number of supports, okay, then depth L by D ratio we will going to assume as 26. So remember this simple rule. If cantilever beam, L by D is 7. If it is simply supported beam, L by D is 20. And if it is continuous beam, L by D ratio is 26. This is the first step in the design. Okay, so L by D you have to assume, then you have to find out the effective depth, that is small d you have to find out. Next, another important point you have to remember, the minimum bars, okay, that is main bar, whatever you are providing main bars in the bottom of the beam, that is called tension steel. The minimum number of bars used as a tension reinforcement should be at least 2. So minimum 2 bars should be there in the beam at the bottom. I am telling about the bottom, that is main steel. So at any condition 2 bars should be there. Okay, then according to design, whatever you may get 4 numbers, 6 numbers, 8 numbers you can provide, but minimum should be 2 bars. Okay, we cannot provide 1 bar, right? So minimum 2 bars should be there, and then according to the design, whatever the number of bars required, that you have to provide at the bottom. Okay, then the next point is the diameter of hanger bars. So what do you mean by this hanger bars? Okay, so if you see the beam reinforcement, so in the bottom main steel will be there, okay, and at the top, okay, if it is a singly reinforced beam, so at the top we will going to provide 2 bars just for the supports. Okay, just for the supports, nominal 2 bars will be provided at the top of the beam. So these 2 bars are known as hanger bars or anchor bars. Okay, the top 2 bars, whatever you are seeing, those 2 bars are called as hanger bars or anchor bars. These 2 are provided for the support to main bars. Okay, so the diameter of hanger bars or anchor bars should not be less than 10 mm. So whenever you are providing the top 2 bars, the diameter of these top 2 bars should not be less than 10 mm. So you can provide 10 mm diameter bar or 12 mm diameter bar. So it should not be less than 10 mm. So this is for hanger bars. Next, the diameter of main bars, that is tension steel at the bottom, the diameter of the main steel should not be less than 12 mm. So hanger bars should not be less than 10 mm diameter, and bottom steel diameter should not be less than 12 mm. Okay, now what about the width? The general width of the beam, small b, width of the beam we have to assume. Okay, so general procedure is, normally we are going to provide 150 mm or 200 mm, 230 mm, 250 mm and 300 mm. So out of these width, anything you can provide. So it is 150 to 300 mm will be the width of the beam. Okay, now important here is depth. Okay, this B we can assume, there is no problem, but D we have to calculate. Okay, then minimum area of tension reinforcement at the bottom. So what should be the minimum area? Okay, minimum bars will be 2. Okay, then if you get the number of bars will be 4 bars, 6 bars, like that. So what should be the minimum? So minimum area of tension reinforcement shall not be less than the given by the following equation. So from this you can calculate the AST, minimum AST, that is AST upon BD is equal to 0.85 upon Fy. So therefore AST is equal to what? 0.85 upon Fy into BD. So from this we can calculate AST, that is minimum AST. So where B and D are the width and effective depth, this B is the width of beam, D will be the effective depth of the beam. Okay, so now simple, this is in the form of AST. Suppose if you want to calculate percentage, what should be the minimum percentage of steel? So when Fe415 grade steel is used, okay, if grade of steel is Fe415, minimum percentage of steel is equal to what? 0.205. Okay, 0.205 into B into D. Okay, when Fe415 grade steel is used, the minimum percentage of steel is 0.205% of B into D. Suppose if you are using Fe250 grade steel, okay, then minimum percentage of steel is 0.34% of B into D. So this is for, okay, minimum percentage of steel for bottom, that is main steel. Okay, so if your grade is Fe415, it is 0.205, and if your grade is Fe250, it is 0.34%. Then last point you have to remember, what is the maximum percentage of steel? So minimum is, from this you can calculate, the maximum you have to calculate, beyond that you cannot provide the bars. So the maximum percentage of tension steel is equal to 4% of gross sectional area of the beam. 4% of what? Gross sectional. Gross means total, that is B into capital D now. Gross area of the beam. So 4% of B into capital D. So that should not be more than that, you should not provide the percentage of steel. So this is minimum percentage of steel, this is maximum percentage of steel. So these are the some important basic points you have to remember before going into the design. Okay, now let us start with the design. First we are going to see the procedure, okay, or what are the different steps to be followed in the design of beam. First we are going to see simply supported beam. Okay, first we will consider simply supported design of beam. Okay, so now what will be the data given in the design? So clear span will be given, okay, clear span of the beam, live load, okay, live load on the beam will be given, then type of support, okay, whether it is a simply supported, cantilever or continuous beam, supports will be given, type of supports will be given, then type of concrete and steel, that is a grade of concrete and steel will be given. Okay, so this is the only thing will be given in the problem. Okay, clear span, okay, live load will be given, and type of support, whether it is a simply supported, cantilever or continuous beam, then grade of concrete and steel, okay, M20, M15, M25, like that, then grade of steel, Fe415 or Fe250 or Fe500 grade steel will be given. Now for this you will going to design the beam. Means what design means, we have to find out what is the overall depth of the beam, then width of the beam and effective depth of the beam we have to calculate. So if you calculate D, okay, then it is possible to calculate the effective depth. So means we are calculating capital D, small d and width of the beam, and important is after finding out the dimensions, you have to find out what is the area of tension reinforcement, okay, main steel. What will be the area of main steel? That is in the form of numbers, how many bars required at the bottom of the beam, that is area of tension reinforcement. Now another important thing is, along with the tension reinforcement, we have to calculate or we have to find out shear reinforcement, shear force. Now see, what is shear reinforcement? Now we know tension reinforcement, we know, okay, main steel we are provided at the bottom, right? Okay, and what is shear reinforcement? No doubt, whatever the bending moment which is coming on the beam, that will going to take care by these main bars, right? But what about shear stresses? If the shear stresses comes in the beam, okay, so to take these shear stresses, we require stirrups. Okay, we require the stirrups or bent up bars. So these stirrups are known as shear reinforcement. Okay, bending moment will be taken by these main bars, but shear reinforcement will be taken care by what? We have to provide the stirrups. Okay, so when you start design, we're going to get this. Okay, how to calculate the shear reinforcement, that we're going to see. First remember, data will be given, then we're going to design capital D, effective depth small d, width of the beam B, area of main steel, that is AST, then shear reinforcement we will going to calculate. Then what are the steps to be followed? Okay, now see here, the first step. Okay, so you have to start with assuming the effective depth of the beam, small d we have to assume. Then how to assume, right? We know already. Okay, just this we have to assume the, first you have to see whether it is a simply supported beam or continuous beam or cantilever beam. Based on that, L by D ratio. Now see, effective span, that is small l divided by effective depth small d. So L by D is equal to 10 to 20. So why 20 it is? If it is simply supported beam, 20 you have to assume, that is 10 to 20. The ratio, I am telling about the ratio, L by D ratio is equal to 10 to 20 for simply supported beam, or again depending upon its load. Now see, so again the small table you have to remember. Okay, so if the span, so there are two spans, clear span. So what is clear span? So this beam is simply supported on these two supports. Okay, so now clear span is inner to inner surface, distance between inner to inner surface of the support is clear span. This is clear span, that is capital L. Now effective span means center of this support to the center of this support is effective span, that is small l. Okay, in the problem clear span will be given. Now we have to calculate effective span. So effective span is what? So clear span, that is capital L plus half of this width, half of this width. So we'll get effective span. So using this effective span, we have to assume L by D ratio is equal to between 10 to 20. Now for again references, now see this span. Okay, span. If the span is between 3 to 4 meter, okay, this clear span is between 3 to 4 meter, then you have to assume L by D ratio is 15 to 20. Maximum is 20 only. So if the span is 3 to 4 meter, you have to assume L by D, small l by small d, 15 to 20 meter. Then if the span is 5 to 10 meter, okay, span is 5 to 10 meter, you have to assume 12 to 15. Okay, then if the span is more than 10 meter, okay, length of the beam is more than 10 meter, we have to assume L by D is equal to 12. Okay, 3 to 4 meter, L by D is 15 to 20. Then 5 to 10 meter span, L by D is 12 to 15. Then more than 10 meter, we have to assume L by D is equal to 12. So L is given in the problem, D we have to calculate, but L by D we have to assume within this ratio, then we can calculate the D. So D is equal to L by this, we will get small d. Okay. Now if you get this small d is what? From top of the beam to the center of reinforcement, that is small d. Then how to calculate capital D? That is overall depth. So small d plus effective cover. Effective cover means from bottom to the center of this steel. So small d plus effective cover will give capital D, overall depth of the beam. So overall depth of the beam capital D is equal to effective depth, that is small d, plus effective cover. Or in general what we can assume, capital D is equal to effective depth plus 50 mm. We have to assume 50 mm means what? It is a clear cover. Clear cover means from bottom to the bottom of steel. Clear cover plus half the bar diameter will get effective cover. So in general what you can say, if you get D, small d, okay, so for capital D is equal to small d plus 50 mm we have to assume. So from this we can get, first step we can get small d and capital D. So this is the first step. So depending upon the span ratio, span length, we can assume these L by D ratio. Calculate small d, calculate capital D. This is first step. Then the second step, now you have to calculate width of the beam. So width of the beam, directly you can assume this beam B, small b is equal to 1/3 of D, that is 1/3 of small d to 2/3 of D. Okay, from D you are going to get first step. Okay, so 1/3 of D to the 2/3 of D. So calculate, we will get the small b. See, so general width will be what? 150 mm or 200 mm, 230 mm, 250 mm or 300 mm. So any values you can provide as a b. If you can calculate this, or directly out of this any one dimension you can take as a width of beam. Then next will be effective span. The third step you have to calculate effective span, that is small l. So here you have calculated in the beginning. There are two criteria now. Okay, effective span is equal to, first criteria is what? Clear span, that is capital L plus bearing. Now see here, this is the clear span. Okay, capital L from inner surface of the support to the inner surface of the support is capital L, clear span. So clear span plus one bearing. Bearing means, okay, this bearing, this is one bearing, support, this is one bearing. So clear span plus half you have to take, means first criteria is what? Center to center of support, from center of this support to the center of this support. How will calculate? Clear span L from this to this, clear span plus half of this support, then half of this support. Okay, half of this plus half of this means it is one bearing. Okay, one width we have to add. So clear span plus one width will give effective span. Effective span means center of this to the center of this. Then second criteria is clear span plus effective depth. So whatever the depth we are going to calculate here, effective depth small d. So capital L plus small d. Okay, so we'll get effective span. So out of these two, whichever is the smaller value, okay, we're going to consider that will be the, okay, the effective span. So two criteria, we're going to calculate effective span. Whichever is less, that will be the effective span of the beam. This is third step. Now fourth step is what? Now we have to calculate the loads. Okay, because depending upon the load only bending moment will going to come. Okay, so first calculate the total load. So what are the loads we have to consider now? First you have to consider self weight of the beam. Okay, its own weight. Okay, self weight of the beam. How to calculate self weight of the beam? So if you know the area of the beam, okay, area means small b, that is width of the beam into capital D. Okay, it is the overall area. Small b into capital D, it is the area, multiplied by density of RCC. The beam is made up of RCC. Concrete will be there, steel will be there. So we have to take density of RCC. So density of RCC is what? 25 kilonewton per meter cube. Okay, density of RCC will be 25 kilonewton per meter cube. So area, that is small b into capital D into 25. Okay, we'll get self weight of the beam or own weight of the beam will be this much, that is kilonewton per meter. Then live load, it is given in the problem. So see how much live load is given, that you have to write down, that is kilonewton meter. So basically self weight of the beam you have to consider, live load given in the problem you have to consider. Then other than this, if you are any load is given, that you have to take. So add all these loads. Okay, add all these loads. This will be small w. Why it is small w? Whatever the load comes on the beam, it is in the form of UDL. Okay, uniformly distributed load. Okay, that's why we are designating as small w. Means it is in the form of UDL, that is kilonewton per meter. So this is total small w. Okay, load. Okay, and this is small w, that is working load. Okay, but what we want factored load. So how to calculate factored load? Whatever this w is there, small w, multiply 1.5. Okay, factored load or ultimate load is equal to 1.5 into w. Okay, we'll get wu now. This is working load, this is ultimate or factored load. Multiply 1.5 to this, we'll get wu. So this is the total load which is coming on the beam. Now for this load, what will be the bending moment? We are going to calculate now. Now calculation of bending moment. Okay, mu. Okay, ultimate bending moment mu or factored bending moment mu. So now again you have to see whether this is a simply supported beam or if it is a cantilever beam. If it is a simply supported beam, so what is the maximum bending moment? WL square by 8. Okay, maximum bending moment will be at the center of beam. So mu is equal to what? WL square by 8. WL square by 8. So this WU into effective span square divided by 8. If it is simply supported beam, maximum bending moment will be WL square by 8. If it is a cantilever beam, if you are designing cantilever beam, mu is equal to WL square by 2, not 8. WL square by 8 for simply supported beam, WL square by 2 for cantilever beam, that is maximum bending moment. Okay, so from this you can calculate the maximum bending moment. Now next step, you have to calculate you have to check the effective depth. Initially we have assumed this, no? L by D ratio we have assumed and we have calculated the D. We have to check whether this D is sufficient or no to take this bending moment. Okay, now equating factored moment is equal to limiting moment of resistance. So this is a factored moment. If you are designing simply supported beam, consider this mu. Whatever the mu will going to get WL square by 8. So that will be the mu here. That is equal to mu limit. Okay, so based on grade Fe415, Fe250 or Fe500. Let us take the grade of steel is Fe415. So this mu is equal to, for Fe415, what is mu limit? 0.138 FCK BD square. So mu is equal to mu limit. Now whatever the mu will going to get here, substitute mu here, 0.138 FCK is known, B is known. Okay, don't calculate D. So don't substitute D here. So calculate D. So D is equal to what? D required. D square it is. So D square is equal to mu divided by 0.138 FCK B. So D is equal to square root of this mu divided by 0.138 FCK B. So from this we are going to get the D required. Okay. So check this D required, means this is the required. To take this bending moment, how much D is required? This. And check this with the D calculated here. Whatever the D we will going to calculate here based on this L by D is equal to this, and D we have calculated. Check this D with required. Okay, so required is this much, and how much you have provided, that you have to check. So if D required is less than what we are provided, is our design will be safe. Okay, if this D required, if you are providing more than this in the beginning, then design is safe. Otherwise you have to go again first step. Okay, repeat the same procedure. Okay. Right, so this is another important step. Now next is, after checking the depth, next important thing is now you have to calculate the area of main reinforcement. So main reinforcement, that is main steel provided at the bottom, we have to calculate. How we are going to calculate? We know already this AST is calculated as follows. So mu we know. So moment of resistance, ultimate moment of resistance here, this mu is equal to 0.87 Fy AST D small d into bracket 1 minus AST upon BD into Fy upon FCK. So solve this equation, you will going to get the area of main steel, that is AST. Or another simple equation is this. Instead of calculating area, first I am going to find out percentage of steel. Okay, in terms of percentage, that is PT. PT means percentage of steel. So how to calculate percentage of steel? So this equation, already we have used this. Okay, so percentage of steel is equal to 50 into bracket 1 minus root of 1 minus 4.6 mu divided by FCK BD square whole divided by Fy upon FCK. So from this we can get the percentage of steel. Okay, that is PT in terms of percentage. So much percentage, 0.2%, 0.3%, like that. Okay, then based on the percentage, calculate AST. Okay, AST is equal to, if you know the percentage, you can calculate the AST. So AST is equal to what? Percentage PT divided by 100. 100 because it is in percentage. Whatever the PT will going to get, this divided by 100 into B into D, small d. Okay, area of steel is equal to PT by 100 B into D. So then we will going to get the AST. Okay, then normally what we require how many number of bars. AST is known, but when you are providing the reinforcement in the beam, it should be numbers. 2 numbers, 3 numbers, 6 numbers, 8 numbers. How many bars you have to provide? So number is required here. So but you know the AST, yes, you can calculate the number of bars. Now we have to assume the suitable diameter of the bar. But what is the condition? Again you have to remember here. So for main steel, diameter should not be less than 12 mm. Okay, so diameter of the main bars should not be less than 12 mm. So 12 mm you can assume. Okay, 16 mm you can assume, 18 mm you can assume, 20 mm diameter you can assume. So if you want to calculate number of bars, assume the bar diameter, then you can calculate number of bars. So number of bars is equal to total AST. Whatever the area AST you have calculated here, this total AST divided by area of 1 bar. 1 bar means whatever the bar diameter you are assuming, 16 mm. If you are assuming 16 mm diameter bar, so this total AST divided by area of 16 mm diameter bar, that is total AST divided by pi by 4 d square. So diameter of the bar we have assumed. So from this you can get the number of bars. 6 numbers, 7 numbers, 8 numbers, that will be the number of bars required for main steel, that is at the bottom. Okay, so remember minimum number of bars is 2. Okay, at any condition you should not be less than 2 bars. Okay, right, this is step. Next, after calculating main steel, another important thing is you have to calculate check the shear reinforcement, whether the stirrups are required. Okay, along with this main bars, stirrups are required or not. Okay, if the shear stresses comes in the beam, okay, we require the stirrups in the form of shear reinforcement. Now as you know, if it is a simply supported beam, when it bends, maximum bending moment will be at the center. Bending moment will be maximum at the center. Then where is the shear force maximum? Shear force will be maximum at the supports. Both the supports, shear forces will be there. So because of shear forces, shear stresses will be there. So to take these shear stresses, shear reinforcement in the form of stirrups are required. Okay. Then how to calculate, how to check whether shear reinforcement is required or not, we are going to check. Now first what we are going to calculate? Calculate the shear force. Okay, calculate the shear force. So for simply supported beam, right? For simply supported beam subjected to UDL, what will be the shear force? Shear force at the support it is, okay, not at the center. Center maximum will be bending moment. At the supports, shear force will be maximum. So shear force at the support of a simply supported beam is equal to WL by 2. So you have to calculate using this equation shear force at the supports, both the supports, it is WL by 2. So W is the total load, L is the effective span, divided by 2, we will get V. Capital V means shear force. Okay, factored shear force. VU means ultimate shear force or factored shear force. VU is equal to WUL by 2, WL by 2 for simply supported beam, or if it is a cantilever, it is WU into L. Okay, shear force. Okay, from this you can calculate the shear force. Next is you have to calculate the shear stress. Shear force is known, you have to calculate shear stress. Stress is equal to what? Force divided by area. Okay, stress is equal to force divided by area. So nominal shear stress means what, how much shear stress is coming on the beam, that you have to calculate, that is indicated as tau V. Now remember another term, nominal shear stress tau V. Tau V is equal to Vu divided by B into D. Okay, tau V is equal to Vu divided by B into D. So this you will going to calculate. Tau V you have to calculate, Vu is known and B into D is already known. So calculate nominal shear stress tau V. Now one more term we are going to calculate, that is tau C. This tau C. So what is this tau C? This is the permissible limit. Okay, maximum shear stress allowed in the beam, that is called as permissible shear stress. So how to calculate this tau C now? So for this you have to refer the table number 19. Okay, to calculate tau C, that is permissible shear stress, go to table number 19. Okay, IS 456 2000. So there will be a table number 19. From that table number 19, some columns are there. You refer those columns, you will going to get the tau C value. So in that first column, in this table number 19, the first column is percentage of steel, that is PT. Okay, so PT is there. So you have to calculate what is the percentage of steel. So AST we already calculated here. Okay, area of steel we have calculated. So this AST will going to provide divided by BD. AST upon BD into 100. Okay, whatever the AST we have calculated, that divided by B into D into 100. 100 is because percentage. So from this we will get the PT. So the first column in table number 19 is PT. So see what is the percentage of steel. Okay, then directly we are going to get the this tau C value. Okay, so we will get the tau C value. Now compare this tau V, that is nominal shear stress, and this permissible shear stress. Tau V and tau C are compared. Now see, first condition is what? If this tau V nominal shear stress is more than the permissible shear stress tau C. If tau V is greater than tau C, okay, then shear reinforcement is required. We have to design the shear reinforcement. So first condition, if this tau V is greater than this tau C calculated, then you have to design the shear reinforcement in the form of stirrups. Now how to design that? Now see, then we have to calculate shear taken by the concrete. No doubt, steel bars, whatever we will going to provide, they will going to take stirrups, they will going to take the shear stresses, but concrete is also taking some of the shear stresses. So small amount of shear will be taken by the concrete also. Okay, so how much concrete will going to take a shear stress? This is tau C into BD. So shear taken by this, or shear force taken by the concrete is equal to tau C into BD. Tau C we have calculated just now. So multiply B into D. So this will give shear taken by the concrete. Then shear taken by the stirrups. How much stirrups will going to take, or shear reinforcement will going to take the shear stresses? So VUS, S means stirrups. So VUS is equal to VU, that is a total shear force minus shear taken by the concrete. total shear force minus shear taken by the concrete will give the shear taken by the stirrup. So VUS is equal to total shear force minus this tau c into BD will get VUS. Now we have to assume the bar diameter for stirrups. Stirrups you have to assume the bar diameter. Okay, so for stirrups it is not less than 10 mm. What we have seen in the important rules. So assume 8 mm or 10 mm. It is practicable. Okay, so for two-legged stirrups, when we start the design, I will tell what is this two-legged stirrups. Okay, so assume 8 mm or 10 mm diameter for the stirrups. So therefore, area of stirrups is equal to this. So area of stirrups is equal to two-legged means you have to multiply 2 here. Four-legged means multiply 4. So 2 into pi by 4 diameter square. If you are assuming 10 mm diameter, it is 2. Two-legged means you have to multiply 2. 2 into pi by 4, 10 square. Okay, so from this we will get area of stirrups. So this much area of stirrups will be required. Then here we are going to calculate spacing of the stirrups. Okay, at what spacing the stirrups are provided, at what distances the stirrups are provided. So spacing of stirrups should not be less than the following 3. So 3 conditions we have to consider. One is spacing is equal to this formula. So all these formulas are there in IS 456. Okay, when you start the design I will tell you how to refer the IS 456. So from this you can calculate the spacing, that is spacing SV, small sv, spacing is equal to 0.87 into Fy into ASV into small d divided by VUS. VUS is the this. So this VUS, then Fy, ASV is this into effective depth of the beam. So one spacing we are going to get. Second, spacing should not be greater than 0.75 into D. 0.75 into effective depth. This is second spacing. Then third spacing you have to calculate. At any condition, spacing should not be greater than 300 mm. Okay, so from this one spacing you will get. Next is 0.75 D, next is 300. So out of these 3, okay, out of these 3, whichever is the lesser value, okay, whichever is the lesser value, that will be the spacing of stirrups. Okay, this is the spacing you have to calculate. Now this is what when tau v is greater than tau c, means shear, okay, tau v nominal shear stress greater than tau c, this procedure we are going to follow. Suppose if tau v is less than tau c, okay, tau v less than tau c, then minimum shear reinforcement is to be provided. Okay, minimum shear reinforcement is to be provided, and assume 6 to 8 mm diameter bar. Okay, and nominal spacing will be provided. But if its tau v is greater than tau c, this procedure we have to follow. Okay, we will see in the problems how to consider these two conditions. Now the next step is we have to check for the deflection. Important is whatever the design we are going to do, that is till now, till this step, whatever we are designed, whether this will going to take a deflection or not, with the deflection is within permissible limit or not, we are going to check. Okay, so this step will be followed. Okay, so note down the percentage of steel provided, PT, how much area of steel we have provided. Based on that percentage we are going to calculate PT value. Then go to again IS 456, that is figure number 5. So there will be a figure number 5 we are going to refer. Then this formula is there, so we are going to use this formula. Okay, then some formula is there. Calculate the modification factor KT for curve, that is refer clause 23.2 IS 456 2000 for PT value. Now this is the formula we have to refer. So for the deflection, so L by D maximum, it is there in the code book also, it is not necessary to by heart. Okay, L by D maximum is equal to L by D basic. What is this L by D basic? Why you have substituted 20? Now in the beginning, so for simply supported beam, okay, what is L by D maximum? 20. So we have to write here. So L by D maximum is equal to L by D basic. This is L by D basic into KT, then KC, then KF. These three terms will going to be comes into picture. 20 into KT, KC and KF. That will be calculated. Now for simply supported beam, so KC and KF are 1. So only we will going to write 20 into KT. So from here we will going to get this KT from this, that is refer figure number 5. Okay. So L by D maximum is equal to 20 into this KT value you will going to substitute, calculate this L by D maximum. So this L by D maximum compared with L by D provided. So in the beginning we have calculated effective span divided by whatever the D we have assumed, that we have to substitute. So this L by D maximum should be greater than L by D provided. Then the deflection is within the permissible limit, or the beam is safe, what you can say that. Right. If this L by D maximum, is less than this L by D basic or L by D provided, then you have to redesign the section. Again you have to go to first step, right? You have to redesign the beam. But so L by D, we have L by D ratio in the beginning we have assumed, always we are in the safe zone. So always this L by D maximum will be greater than the L by D provided. So this is the check for the deflection. Now your last step is what? Whatever the sketch, that is whatever the reinforcement you have calculated, B you have calculated, effective depth you have calculated, shear reinforcement you have calculated. So all this should be shown in the form of sketch. So you have to draw two sketches. One is longitudinal section, that is lengthwise. Then you have to draw cross section showing the reinforcement detail. So finally we are going to draw longitudinal section of the beam and cross section of the beam. So totally remember there will be 10 steps. Okay, design, there you have to follow the 10 step. So the design is simple. Okay, stepwise you have to remember. So there is no question of by hearting anything here. So IS 456 is there. So from that you have to design the beam. Okay, so in the examination we will going to get one full problem of 20 marks. Okay, there will be only one problem, design. Okay, so it will be 20 marks problem, either singly reinforced beam design, cantilever beam design or T-beam design. Okay, so these three will going to get in the examination. Okay, so this is the procedure you have to follow. I hope you have understood this steps. So when you start the problems, again will in detail we'll going to discuss. Okay, so thank you very much for attending this session, and the next session will start with the design problems of singly reinforced beam. Okay, so thank you very much.